Hello everybody, and welcome to the ACCESS Habitable Planet program online course. I am Neville Sweijd, and I am the director of the ACCESS program. I work with Carl Palmer, who's really the brains and the tools and the efforts behind the Habitable Planet workshop. And I'm just going to give you a brief introduction and tell you about the exciting program that you're going to be part of. I should emphasize, of course, that Habitable Planet as a program has been running now for several years. We've had almost 1,000 people pass through us, and we have a very vibrant community. And I'm very excited that so many of you have signed up to do this online course. Firstly, just to say that ACCESS is a program of the National Research Foundation. We have many partners, as this slide that you can see demonstrates, partners from all over the country. We have about 100 postgraduate students and many professional scientists that work with us all together. But I thought I'd start by telling you a little bit about me, because I've had a career in natural sciences as a postgraduate student and as a professional. And I started my career as an undergraduate at UCT, and then a postgraduate at Rhodes University, and then again at UCT. And I'm a marine scientist. I first worked on sea urchins. You might be familiar with those. We have one or two species. In fact, we have more than one species along our coast, but that's the very common one. And then I did my PhD on abalone, perlemoen, and you can see, you might know them as an ashtray. But they're a very important species, a very valuable species from a fisheries point of view. And I worked in molecular applications in marine science. And these were two incredibly enriching experiences as a postgraduate student. But then I went on to work elsewhere. I worked at the University of the Western Cape at an institution there. And we did lots of different projects, some community projects in the marine world. The project I'm most proud of all the things I've done is a cookbook, which we did with the community of Saldanha Bay, from the women who work in the fish factories, who have had generations of experience. So we did a history of the community, and we produced a cookbook, which was really great. And then I moved to Namibia, where I worked on the west coast in a program called Benefit, which was a program dealing with the fisheries and environment along the Benguela Current. And after that I joined the CSIR, and then I joined ACCESS, and now I am the director of ACCESS, and this is what I look like. No, not really, you can see me in the corner. Okay, just a little bit more about ACCESS to tell you that we've produced a lot of outputs, and these are all available on our website if you wanted to know more. And we're hoping through this course that you will all consider pursuing higher degrees in science, in natural science or in other kinds of science. And if you read some of this material, you'll see some of the stories of some of our students who have passed through the program. What we're really trying to do is understand the Earth system, and this is really what you'll be learning about, the Earth system in its broadest sense, the interactions between the ocean's atmosphere and land that drive the Earth system, and how it has changed over time, geological time periods and recent history, and how it might change in the future. And as you'll learn, our species has really been on this planet for a very short time in the history of the planet. To do this, we need to understand the various components of the Earth system, for example, biogeochemical cycles, or climate systems, or the hydrological system, or even how humans interact, like land use, land cover changes, and changes that have been imposed by a variety of different reasons. And the outcome of this are a whole range of applications. And each of these stages, in both looking at either one of those inputs or looking at the system as a whole, trying to model it, or working on the applications, is really the scope of what we try to do in the program. So just to drive this point home, I've shown you here 5 bubbles. Each of those bubbles are part of a theoretical framework. The top left bubble, which says drivers, if you think of the Earth as a superstructure, it has continents, it has ocean currents, it has atmospheric systems. This is how the Earth is constructed. It hasn't always been the same in geological time periods. It was different planets some time ago, some millions and millions of years ago, or billions of years ago. But at the moment, this is the structure, and it's if we like, we can call it the superstructure. And the next bubble represents processes, such as the biogeochemical cycles or the hydrological cycle. And that's really the infrastructure of the Earth. And these two are interacting, and they are very dynamic. And you will learn about how these interact with each other to produce our dynamic Earth system processes. The next is what this dynamic has, what impact it has on the state of the ecosystem. And by ecosystem, I mean both the natural ecosystem as well as the social and ecological ecosystem, the human ecosystem. So this dynamic Earth system, which is changing all the time over different time periods, has impact on the state of the ecosystem. And the changing state of the ecosystem has impacts on our society. So, for example, it impacts on health, it impacts on agriculture, it impacts on retail, it impacts on all sorts of services and things we take for granted. And ultimately, then, there are responses. What can we do to try and intervene or manage this dynamic system? And so the different interventions which we can put in place are either at the driver level or the process level or the state level or even at the impact level. Now, interestingly, this all happens in a closed system. The Earth is one closed system. But, as you might or might not realize, it is influenced by something outside of our planet. And that outside of our planet is our sun. We're in a solar system. And the sun's influence on the Earth system happens at different time scales. At very long-term time scales, the Earth's orbit is not always the same, so our summers and winters are different. Similarly, the slope of the axis of the Earth's, as you know, is tilted. That tilt changes, and so a combination of these long-term changes have an impact on how the sun influences us. But right now, the sun has a winter and a summer extreme in the southern and northern hemisphere interchangeably, and that's very important because every year this causes a climate change. We have a climate change from winter to summer, and they're very radical climate changes. You'll know yourself, especially living where we do in South Africa. So what we are trying to do with the program now is to understand the seasonal cycle. I'll explain this in a bit more detail now. And how does the influence of the seasonal cycle influence this whole Earth system, right from drivers and processes through state impacts and to our responses? That's really what our science is all about. And we are looking at this in a number of different ways. In the geophysical sense, we try to look at the climate models and understand how the models are working or not working, as the case may be, how useful they are. For example, we're trying to understand how the Earth system impacts ecosystem state on a different set of timescales, and so on. Just to drive the point home, if you look at this sine wave here, this would represent a typical seasonal cycle. Of course, it's never as ideal and as stable as this. And the red lines at the top represent how we are adapted to this. So we know what kind of winters, what kind of summers we usually get, even extreme ones, where we live. And this is very different in different parts of the world. The dotted line represents, the red lines then represent our adaptation envelope. How well adapted are we to that changing signal? And the dotted line represents your economic disadvantage. If you're a poor person or you live in a poor household, your ability to cope with even so-called normal summer and winter fluctuations or extremes of the seasonal cycle is impaired. Now, all of our government services, all of the things we take for granted are really adapted to the seasonal cycle. Our society's evolved to cope with this. Agriculture, as I've said, mining, energy supply, tourism, transport, health, retail, all of these are adapted to the seasonal cycle. There are winter seasons and summer season sales, or whatever the case may be, as you are probably aware, but haven't really thought too much about. And things like floods and fires are very seasonal, for example. And ecosystems, plants and animals and ecosystems in general are adapted to the seasonal cycle. And there's a concept called phenology, which explains the timing of the life cycle of organisms, which is adapted to the cycle. Now, that cycle is not stable. And sometimes we have extreme events. Sometimes we have an extraordinary event, such as the El Nino of last summer, or a very cold winter, as the case may be, or a very hot summer, or a drought. And these are called extreme events, and when they happen, then the natural fluctuation of the seasonal cycle exceeds what we are adapted to. And so we see damage to infrastructure. If you're poor, your ability to cope with these extreme events is also compromised. So this is also a socio-economic consideration as well as a natural phenomenon. And then at the bottom, we see global change forces such as damming of rivers or canalizing of rivers or urbanization and changes in our society reduces our resilience. So we have the combination of the extreme event and the reduced ability to cope impacting on us in this way. And so what we really want to stress here is how the seasonal cycle is such an important way to look at the world. And this is the kind of theme we're using. So I'll just give you some scenarios. As you know, with climate change, people talk about the annual average changing. If the climate's extremes of summer and winter, which is really how climate change manifests, with the extreme changes, the annual average tells us nothing about how much hotter our summers are compared to other summers, or how much colder our winters are, or wetter our winters are relative to others. So looking at the seasonal extremes is more important now than just considering the annual average. We might see, for example, a change in the nature of what were or are regarded as typical summer and winter variation. So it's variation of the seasonal signal over long-term time periods that becomes important. And then we see things like perturbations. Last summer we had the extreme event. Sometimes these cycles are longer, and perhaps combinations of the two. So the annual average tells us something, but unless we look into the seasonal cycle in more detail, we won't really understand how climate variation and even climate change interacts with society and with the natural Earth system. And that's really the focus of our research, and I hope that during this course you will learn more as we go along. Just one example to illustrate this is work that I've become involved in. So what you're looking at is a graph from the Western Cape, and in the blue lines is the incidence of diarrhea in the Western Cape, and in the red bars you will see the incidence of pneumonia in the Western Cape. And then the lines, the red and blue lines, represent the variation in the maximum and minimum temperatures over the year. And really what this shows, it's actually an anomaly, which is the departure from average. What you're seeing here is that in January, February, March, that's when we see a positive anomaly. So we see more diarrhea than we do in the rest of the year. That means that diarrhea is really a summer disease. And if you look at the red bars, you'll see pneumonia peaks, or if you like, it's positive in the winter months, which says this is a winter disease. So you might or might not know, this is true in other parts of the country, that diseases, for example, are seasonal. So the question is, if seasons are not the same, can we see differences between the incidence of disease in one season compared to the next season, and what explains this? So this is what we're looking at right now, and here's a plot of the long-term data series of diarrhea in the Western Cape and temperature. You can see how as temperature goes up in the summer, the disease peaks, and some years are more than others. For example, you can see here the last summer season is actually higher than all of the others, probably due to the higher temperatures that we received in the Western Cape for an extended period of time. And if you plot these, for example, you can here plot the minimum and maximum temperature against a measure of the incidence, you get very high correlation. So what this means is we can mathematically predict what temperatures will produce what amount of disease. And we can also then make predictions about if temperature increases, what can we expect to happen. And this we can use, if you like, as an early warning system on a seasonal basis, or as a long-term examination of scenarios under climate change. So this is how you can apply this science. Just a quick little addition. This is data from Gauteng, and you can see in this middle of this data there's a lot of diarrhea occurring at the middle of this data set, which actually means that even in the winter, that winter was actually more than normal for a winter. So something happened then, And if you look onto this graph, here you see minimum and maximum temperature, maximum temperature in the red line, and in the blue line you see rainfall figures. And coinciding with that particular event where we had extra diarrhea, we have lower rainfall. So this implies that rainfall is somehow important in reducing diarrhea, and when there's less rain, there's more diarrhea. At least that's our theory. Now we have to go and do the research to test it. So finally, I just want to show you this graph, which is a graph of the interannual variation in pneumonia in Gauteng. So on the left-hand side of the half of the graph, you can see it's very positive, the blue bars, and in the second half, you can see that it's quite negative. So what it's showing is that there's been a trend in the incidence of pneumonia actually getting less over the years of this particular data set. And in the red line, you can see the minimum and maximum temperatures. And the theory is the warmer it is, the less diarrhea it is. And if you look at this graph, you can see where you get above, this is an anomaly, meaning a departure from average. So when you get high peaks in the temperature, you get low peaks in the diarrhea. And on the whole, if you eyeball this graph, you can see more higher temperatures towards the end and lower pneumonia, kind of confirming this hypothesis. Again, requires more research. Just to point out that these two 0 points are at different places, so it might look a bit odd to you. So all I wanted to illustrate to you was that there's lots you can do. I happen to work in the area of applications and the impact of change and variation, but there are people that are looking at the fundamentals of climate systems. There are people looking at how ecosystems are responding to climate variability and climate change, and there are people looking at the politics and the policy of how to deal with these kinds of problems. And I hope that this example has illustrated to you the kind of exciting stuff that's available out there, and I hope that you really enjoy the course, and I hope that you learn lots, and finally I hope that you consider, after having completed the course, to pursue careers in science and technology. So, thank you very much. I think I'm done. There actually was another graph, but we'll leave that. That's just a correlation, and I'll leave it there and say thanks and cheers.